Today we cover transformations. And transformations, the math code, because that's what it is. It's a code. It's a secret code that lets you take the basic functions that I have graphed here, I have pictures of them, and move them around and change their shape. It's like coding a computer. It really is a code, but it existed long before computers as we think of them. So let us take a look here. These are the basic functions, the ones we start with anyway. Y equals x, y equals x squared, y equals x to the third, y cubed, y equals x cubed, y equals the absolute value of x, y equals the square root of x, and y equals the cube root of x, and you can get all these from your graphing calculator. Yes, you can. Okay, what we're going to do first is we're going to talk about functions and the argument of a function. The argument of a function is wherever the x is. Okay, and you kind of imagine parentheses around it. So for y equals x, the argument is the x. For y equals x squared, well, the argument is the x. For y equals x to the third, the argument is the x, and on and on and on. For y equals the absolute value of x, the argument of the function is x. The argument of the function is always with x. The argument of the square root function is x, and the argument of the cube root function is x. In other words, underneath the radical in both of these. Up here for absolute value, inside the absolute value bars is where the argument is. And for y equals x, x squared, and x to the third, the argument is inside imaginary parentheses, not imaginary, but sometimes imaginary. Like here, you're not going to be using them. But that is what the argument is. Numbers that are inside the argument affect the x coordinate of points. Arguments that are outside, as you'll see, affect the y coordinate. So here is how I would code, how we would code. Moving up. Let's say up 5 units. Then I would have, let's change this to f of x. F of x equals the argument x plus 5. How about x squared? Well, f of x equals x squared plus 5. F of x equals x cubed plus 5. And so on and so forth. To move any function up, you go to the far right side and write what you want to do. So for instance, if I wanted to move these down, I would say f of x equals x, how about minus 3? Down 3. Minus 3. F of x equals x squared minus 3. Minus, that's a minus sign. F of x equals x cubed, equals x cubed minus 3. And so on and so forth. Let's do this for all of them. F of x equals the absolute value of x, and if we're going up 5, there's a plus 5 on the far right side. If we're going down 3, that would be f of x equals the absolute value of x minus 3. So plus means up, minus means down. It's all very obvious and very easy if you know where to look for that particular code. F of x equals the absolute value of x plus 5. We're going to actually look at this in the graphing calculator. F of x. I guess I should have called it g of x, but oh well. The square root of x on the outside of the radical, minus 3. On the outside of the radical, plus 5. You have to be very, very careful not to put your plus 5 or your minus 3 underneath the radical, because that's the argument. That affects the x coordinates, which move sideways. We're talking about vertical, which is up and down. F of x equals the cube root of x plus 5. F of x equals the cube root of x minus 3. That's how you'd code it. Let's take a look at what happens. Okay. All right, how about, well, let's start with x plus 5. X plus 5. Oh, no, graph. Now that's not very good, so I am going to increase the size of the window, -10, yeah, down 10, -10, down 10. Now let's graph it. Much better, much better. Now, what about the basic graph? Where was the basic graph? Okay, let's move down to the red. Actually, it would be better to move up here and clear that. And instead, I'm going to let the blue be the basic graph. Y equals X. Let's take a look at that. That's our basic graph, Y equals X. Now, if I want to shift this up 5 units, I'm going to go to Y equals, I'm going to go down to Y2, and I'm going to say X plus 5. Graph. There's the shifted graph that now is up 1, 2, 3, 4, 5, directly up. We move directly up. Well, what about x minus 3? Let's take a look at that. That one's going to be black, that graph. I would like to change it, but I haven't changed it yet. X minus 3. Graph. There it is. That's shifted down, x minus 3, down 1, 2, 3 units. Let's do the same for the square root of x. Actually, we don't have to. We could do it for x squared. How about the absolute value of x? Because you need to have some practice working with the absolute value of x. All right, how you get to it? You push the math button and then the right arrow key. And that gives you ABS, which is the absolute value. Now I'm going to put my X in there. And then, very important, move to the outside of the argument. And then put a +5. Graph. We have moved the absolute value graph up. 1, 2, 3, 4, 5. Now, if you have the older operating system, this is how you would do the absolute value. Why? This is what you would see. ABS. What you do is you put the X and then close your parentheses. Very important. Now, if I want to move the absolute value 5 units to the right, instead of this, which is what I would have in my calculator, you probably, if you have the older system, let's see, f of x equals abs x, close parentheses, plus 5. Over here, f of x equals abs x, close parentheses, minus 3. Okay, always on the far right. Now, both of us, people with the newer system and people with the older operating system, have both got to make sure to the calculator, absolutely sure that you are on the outside of the argument, not on the inside of the argument. The inside of the argument is in these parentheses. The outside of the argument is either in back or in front. So, how about x squared? We're going to move x squared down 3. Well, wait. So here I am. I have just moved that up 5 units and completely forgotten my color coding. So I'm going to go back to y equals. I'm going to use the right arrow key, come over here and delete. So that now all I have is the absolute value of x. Here's the basic graph. It's a V. The only V I know of is the absolute value graph. Now I'm going to move up 5. So I'll come down here and I will have math, right, enter, X. And then with the older operating system, you close your parentheses. With the newer operating system, you have to hit the right arrow key and move out to the right. And I put my +5 out there. Very important. You'll see what happens if you put it in, put the +5 in there. You'll see that in just a minute. Okay, graph. There's the shifted up graph of y equals the absolute value of x. Now let's do the shifted down. Math, right, enter, X. Come to the outside, the right side, minus 3. This one's going to be black. There it is. We shifted This one down 3, that's where the minus 3 was. This is where the plus 5 was, and this is just the absolute value of x in its home position right there. The v comes to a point at 0, 0. And that would be true for all these basic functions. You can shift them up, you can shift them down. You can shift them up, you can shift them down. Shift them up, shift them down. They don't get skinnier or fatter, but they will go directly up or directly down. Does someone want to say something? You are welcome to do so. Okay, well, now's the hard part, okay? That is the only really easy part. No, I take that back. There's one other fairly easy part. But this is not one of them. Horizontal shifts are not what you expect. Okay, for y equals x, we're going to leave that out because I need parentheses for this. Here's y equals x squared. If I'm going to shift it left or right, that means I have to have parentheses. Because shifting left or right affects the x coordinate, not the y coordinate. Oh, f of x. I'd rather call it f of x. You don't have to, it's not a big deal. Y and f of x are the same thing. Okay, and then f of x. You see the basic format here of moving left or right or doing anything that affects the x coordinate. The x coordinate determines horizontal location. Okay, now we are going to go to the right. Oh, left. Okay, we're going to go left 2 units. Left 2 units. And this is going to be y equals x squared. So if we go left 2 units, we're going to go 1, 2. That's not hard. Then we're going to go right 5 units. 1, 2, 3, 4, 5. So let me write that here. Okay, left 2 units. And right 5 units. Okay. There. Okay, I'm just hearing some scratching from somebody's computer. Okay, now, here's the x. Here, we're going to go to the left 2 units. Now, to me, left means negative. Right means positive. But not here. It's totally the other way around. I'll explain why in a minute, but right now, let's just do this. If I want to go left 2 units, I've got to hit a +2. And if I'm going right 5 units, that has to be -5. Not what you'd expect. Not what you'd expect at all. Let's do this with the calculator. There is a reason for it. Okay, y equals, I'm going to clear, I'm going to clear, I'm going to clear. So the basic function that we're dealing with here is x squared, y equals x squared, and here it is, in its home position. The vertex is at 0, 0. Now, I want to go 2 units to the left. I come down here, parentheses. I want to go left, so I have to say plus 2 squared. Now, I'm going to graph. I've just moved y equals x squared to the left 2 units. Now, I'm going to take y equals x squared and shift it to the right 5 units. Okay. Boom, boom. Okay. Parentheses, x. I want to go right, so I'm going to say minus. This is going to be the black graph. There we are. We move the basic blue graph over to the right 5 units. Why does this happen? Well, here's why. Come down here and let's take y equals x squared. And move it to the right, left. Move it to the left 2 units. Why that happens is that here the origin is right there, okay, at 0, 0. When we shift a function, what we're really doing is we're moving the origin 2 units to the left. And we're moving the origin, if we go to the right, over to the right. The X and the Y axis. Now that's the technical reason, and I found, when I was a student, I found that really hard to understand. So there's a trick to always know what to put in here, or what it means to translate it. Take whatever is in the argument. Here it's x plus 2. And set it equal to 0, because it used to be there at 0, 0. Now you're shifting it. Solve for x. That's where x moves to at the vertex. What you're doing is you're shifting the vertex, and the rest of the parabola has to follow. This tells you where the vertex has moved to, or the most important part has moved to. See, you would think you're moving right, but you're actually moving left. If you take a minute to do this, you will not make a mistake. Over here, when we went 5 units to the right, we said minus 5. Well, take x minus 5 out and set it equal to 0. Now, add 5 to both sides so you can solve for x. There is where the vertex is going, to x equals positive 5, which is 1, 2, 3, 4, 5 right there. There. Or there. Now, let's do it with one more. Let's do it with the square root of x. Clear. 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 Okay, now how I would code this for y equals the square root of x. If I want to go 2 units to the left, see, it's underneath the radical, which is where the argument is. A +2 out here would make it go vertically up, but a +2 in here makes the graph go horizontally to the left, 2 units. And then over here to move 5 units, f of x, 5 units to the right, I would have the square root of x minus 5, definitely under the radical. Not squared, that's silly. Okay, here we go. Second x squared gives you the square root sign, and I put an x. And then I have to use my right arrow key to come to the outside. And I'm going to graph that. If you have the older operating system, see, the older operating system would look like this. Hello. Move. You'd have y1 equals, you'd have a square root sign, but then you want to have that afterwards. It's not underneath, but the way the calculator codes, that means, even though the x comes after the square root sign, anything in parentheses is the argument. So it's the same thing as saying this. It's just the older way of saying it. Okay, so now that, have I graphed it yet? No, I haven't. We're going to graph the basic graph right there. That's y equals the square root of x. Now I want to move 2 units to the left. So I come down here. Second x squared, x plus 2, and then jump to the outside. Outside is for the y's, inside is for the x's. Let's graph this. See, you moved over to the left too. We wrote +2 in the argument, and that moved us to the left 2 units. Now to move this graph, the blue graph, to the right 5 units, I come back here, I come down to y3, and I take second x squared, x minus 5. Jump to the outside. Then graph. There you go. We took this guy and moved it over to the right, 5 units. That's a horizontal shift. And this would be true for all of these. F of x equals x plus 2 to the third power f of x equals x minus 5 to the third power. And one more, because I know I will well, I don't know. Absolute value of x plus 2. Inside the absolute value bars is where the argument is. F of x equals the absolute value of x minus 5. And then, yeah, let's just do all of them. F of x equals the cube root of x plus 2 if you want to go left 2 units. F of x equals the cube root of x minus 5. My cat was just chased inside by big blackbirds. Happens every day. Okay, that's horizontal shifts. So we coded for vertical shifts. We coded for horizontal shifts. Horizontal shifts are sideways. Vertical shifts are up and down. Now, vertical expansions. Imagine a terrible scene. Imagine some terrible kid grabbing a bunny's floppy ears, and a flop-eared bunny, obviously, grabbing the ears and pulling the rabbit up. That's what an expansion is. You take the graph with your hands and you stretch it up. Okay, I'm going to write the basic graphs, functions. Okay, so the basic functions. And then what we're going to do, what should we do? I think we're going to stretch the graph by a factor of 7 is pretty extreme, but let's do it. Stretch vertically. I'm trying to word it the way your book usually, well, my math lab usually words it. Stretch vertically by a factor of. That's the way it words it. Did I say 7? Yes, I did. Okay. Okay, basic function, y equals x, we're not going to use that much. Actually, we are here though. Y equals x squared. Y equals x to the third. Y equals the absolute value of x. Y equals the square root of x. And y equals the cube root of x. The vertical stretch and the vertical shrink all deal with the y coordinates. So they're outside the argument. Here we go. If I want to stretch all of these basic functions, the graphs of all of the basic functions, by a factor of 7, this is what I do. Okay. This pulls the graph up. So here we go. We're going to graph a, well, we're going to do it for all of them so you can see all of them. No, we're just going to do stretches here. Okay, so y equals x, that's your basic function. Now, y equals 7x. Much more steep. That's because 7 is multiplying all the y coordinates, leaving the x coordinates where they are. So here we have 1, 1. But now look, at x equals 1, we have y equals 7. The y coordinate was multiplied. The x coordinate hasn't moved, but the y coordinate was multiplied by 7. Okay, now let's do this for x squared. There's y equals x squared. Now I'm going to stretch it by a factor of 7. Look how skinny it is now. That's because it got the, I can't help but think of rabbit's ears. You're pulling up each arm of the square root graph, and that of course makes it skinnier. You don't change the points. I mean, 0, 0 still stays at 0, 0, but you're stretching it up. Okay, y equals x to the third. And 7x to the third. Okay. There's your basic graph right there. There is a creature, I think, on the outside. Okay. Okay, now, y equals. This is much more steep because you're pulling up on the upper arm and down on the lower arm. Okay, so now I'm going to clear because we're going to do absolute value next. Let's see. Okay, go back to y1, math, right arrow, enter, x. There's the home graph, the basic graph at its home position. Now I'm going to stretch it, not move it, but stretch it by a factor of 7. So 7, math, right, enter, x, jump outside. Okay, graph. Look how much more narrow that is. All right. Now, this is pretty important, which is why I'm going to all this trouble with with that. We're not going to go to quite as much trouble next time. Okay, that was absolute value. Now, how about the square root? Y equals the square root. Up here, square root. Second x squared, yeah. So here's our square root. Now, we're going to stretch that baby by a factor of 7. 7 square root of x. That's 7 times the square root of x. That's being pulled really far up. Okay, now let's take a look at what happens to the cube root. I actually don't know, so I'm interested in finding out. Clear and clear. Cube root is inside math. There it is, it's down here, right here at number 4. So I put an X there, and we're just going to look at the basic graph. And now we go down to Y2, and we're going to say 7 times the cube root. Woo! Look at that. That's some stretching. I haven't done that before. You're the first. You're the first class I've done that with. Okay, so that is what vertical stretching is about. And where you've got vertical stretching, you've got to have shrinking. That is, instead of pulling up, you squish down. Now, the trick to squishing is this. The number you multiply has to be a number between 0 and 1. In other words, a fraction or a decimal, a proper fraction though. Can't be bigger than 1, not 1 or bigger than 1, not 0 or less than 0. So how about making this, instead of 7, I'm going to insert a decimal in front of it so that I have 0.7 times the square root of x. And we are going to shrink it. I'm going to make it disappear for a minute. There it is. There's our basic graph of y equals x to the third. Now I'm going to squish it, shrink it. But it's really squishing. Okay, so come back here, come down here. Well, not that much of a difference. We squished it, but by 0.7. So you're not going to get squished as far. Okay. Let's go down to where the contractions are. I feel like making a joke about childbirth. Contractions. They're not fun. Okay, so y equals x, y equals x squared. y equals x to the third. I really don't have to keep doing this. Y equals the absolute value of x. Y equals the square root of x. Y equals the cube root of x. Okay, I am going to shrink the basic function, shrink by a factor of. How about, I want to make sure it's visible. Instead of 0.7, how about 0.5? That's 1/2. Then how you would write that would be this. Y equals 0.5x, f of x equals, same thing. F of x equals 0.5 times x squared. F of x equals 0.5 times x to the third. F of x equals 0.5 times the absolute value of x. F of x equals 0.5 times the square root of x. F of x equals 0.5 times the cube root of x. Okay. You should hopefully memorize what these look like, because there are also icons that you have to choose when you're graphing that tell the calculator what it's going to graph, or the computer, MyMathLab, what it's going to graph. Anyway, let's do this. Let's take y equals x. I'm not going to do all of them. That's just too boring. Okay, we're going to shrink this. Notice that the shrink factor for a straight line is the slope. .5x. And it's lower, it's been smooshed. Okay, shrunk. Not terribly exciting though. Let's find something more exciting. How about x squared and the square root of x? Okay, so y equals clear and clear. 0.5 times x squared. No. Delete, delete. The blue one is the basic graph. Y equals x squared. Okay. Now we come down. And we're going to do 0.5x squared. Yeah, we've made it lower. That's because all of the all of the y numbers, all of the y coordinates have been multiplied by 0.5. Let me show you what happens when you multiply a number by 0.5. Well, how about nah. If I take the number 10 and I multiply it by 0.5, I get the number 5. because 0.5 is 1/2. If you multiply a number by a proper fraction, you get a smaller number. So the y coordinates have gotten lower. Okay, one more. 0.5 times the square root of x. And then we're going to do something different. A different kind of transformation that's much more dramatic. Okay. Now, square root of x. Basic graph. There it is. Now, we're going to shrink it by a factor of 0.5. Okay. It's lower. It hasn't really changed shape, it's just lower. And that's the effect of shrinking. The sides get closer to the x-axis. Yeah. All right. If you're wondering how you're going to possibly remember all of this, flashcards. They are absolutely, I've been there, flashcards. Not the kind on your cell phone, but actually go to Walmart or Target and buy some flashcards. Actually, they're all over the place everywhere right now. Yeah, some 3x5 cards. Put a different fact on each 3x5 card. Look at them every day. Or every night before you go to bed. Really help you memorize all this stuff. Okay, clear and clear. Notice that the stretch and the shrink actually change the shape of the graph. Now, reflections. All of these graphs can be turned upside down. They can be reflected. When you turn a graph upside down, what you do is you reflect it across the x-axis, and that's what it's called. A vertical reflection is also called reflecting it upside down, but officially it's called a reflection across the x-axis. Let's just take y equals x squared, and y equals the square root of x. They'll give the most dramatic results. So y equals x squared, and y equals the square root of x. Now I'm going to reflect them across the x-axis. Here's how I do it. F of x equals negative x. F of x equals negative x squared. F of x equals negative the square root of x. You stick a negative in front. And we could do that to all of them. But in the interest of time, let's just do these. Okay. Y equals x. Let me make sure you can see this. Y equals x. Graph. Now, I'm going to reflect it across the x-axis. So I'll put a negative sign in front of the x. Woo! Use your imagination and you can see it flipping upside down. That would bring the bottom side up and the upper side down. Now, did I say x squared? I forget what I said. Yes, x squared. Okay, so we'll turn this to x squared. Square, square, there it is. And I'll come down here and make that temporarily disappear. There's y equals x squared in its home position. Now we're going to reflect it across the x-axis, that is, turn it upside down by putting a negative in front. There it is. It got turned upside down. Now we'll do the square root of x. So there's y equals the square root of x in its home position. Now I'm going to flip it upside down. That is reflected across the x-axis. Negative the square root of x. Graph. There we go. So you reflect upside down. You can turn something upside down just by sticking a negative sign in front of it. What that does is it multiplies all the y coordinates of all the points by -1. Okay. Oh, hello, little sheepies. Okay, what about a horizontal reflection across the y-axis? You won't be able to see this because it has symmetry, so when it turns around, it'll look exactly the same way, and I do want to save time. So, what is most visible is the square root of x when you do this, or the cube root of x. So let's do this. There's our basic graph, and we're going to reflect it now across the y-axis. Watch how we do this. Notice these, where you go from here to here, these were vertical. That means only the y coordinates were affected. So that negative sign is outside the argument. But now, a horizontal reflection across the y-axis affects the x coordinates. So that's going to be inside the argument. The square root of -x. Let's take a look. Here's the square root of x, home position. Now, I want to shift horizontally across the y-axis. Yes, square root of negative x. See, here's your basic graph, and now this is the mirror image on the other side of the y-axis. This is a sideways or horizontal reflection. It's a reflection across the y-axis. So the trick is to get inside the argument. You put your negative sign in front of the x. Okay. Now, sometimes there is such a thing as a diagonal reflection. That's called a reflection across the origin. Here's how you do that. And I'm going for the most visible instance. If I want to make this appear down here, that would be a reflection across the origin. So let me take y equals the square root of x, and I want to reflect that across the origin. Here's how I do it. Okay, there's a negative sign in front and a negative sign on the inside. Let's take a look. Okay, square root of x. Is that what I want really? Yes. Okay. So there's the graph of the square root of x in its home position. Now we're going to reflect that guy so that it's a mirror image diagonally across the origin. This is the origin, 0, 0. Negative square root negative x, jump to the end. Graph. There you go. Looks almost like the cube root of x. Here, this became its mirror image down here. And all you're doing is you're just coding the function. You're doing weird things to the function. Okay, finally. Horizontal expansions and contractions. See, what should we choose for a horizontal expansion and contraction? I need something that'll be visible, and I think The absolute value function? Yeah. Okay. I really think that would be better. I don't know why. But no, we're going to do this. We're going to do this. Y equals the absolute value of X. That'll be our basic function. And now once again, stuff in the argument, remember it's horizontal, it's a horizontal expansions and contractions. Okay. So an expansion, which would be a stretch, a horizontal stretch, and a horizontal shrink. That's like an accordion. This is a contraction, this is an expansion, this is a contraction, this is an expansion when it's horizontal. You're smushing together when you've got a horizontal contraction. You're spreading apart when you've got a horizontal expansion. Boom, 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 boom. Okay, how do you get a horizontal stretch? Well, let's look at the vertical stretches for a minute. Okay, here's a vertical stretch. To stretch vertically, you have to put a number greater than 1 in front of X. That's a lie. You put a number greater than 1 on the front of the argument. A number greater than 1, multiplying, if you will, a number greater than 1 in front of the argument. Here it's easy to see the argument. And there's a 7, which is a number greater than 1 multiplying it. That's how you vertically expand, vertically stretch. Now we're going to look at how you horizontally stretch. There we go. A horizontal stretch. Horizontal means you're using the X's, so it's inside the argument. And instead of being a number greater than 1 in front of the X, it's a number between 0 and 1, like, say, 1/2. I could put a fraction, but let's put 0.5. That's the opposite of what it was to be a vertical stretch. Now, to have a horizontal shrink, when we had a vertical shrink, you had to put a number between 0 and 1 in front of the function, in front of the argument. To have a horizontal shrink, you've got to put a number greater than 1 in front of the X, but in the argument. Let's look and you'll see. Okay. Absolute value of x, basic function. Math, right arrow, enter. Okay, so we'll just put an X there because we're doing the basic graph. There it is, the ultimate V. Now I am going to horizontally, what am I doing? Horizontally stretch. Am I stretching? Yeah, it's not at all what you'd think it would be. And I have to actually stop and remember. Okay, y equals, we go down. This is going to be a horizontal stretch. Math, num, enter. Now, instead of x, I'm going to have 0.5 times x, or now, 0.5x. Now, I know it looks lower. However, what's happening here is that 1 has been multiplied by 2. How did that happen? So, but the y coordinate there has stayed the same. So now the y coordinate at 2 is 1. It's only the x's that are not multiplied, but divided. Yes, totally strange. Totally strange. Here's what's happening. If you go over here, we've got some points over here. Let's see, 0, 0, 1, 1, 2, 2. It's just easier to do this with the whole numbers. Okay, now, whatever this number is, it divides the x coordinates but leaves the y coordinates alone. So, this will make 0, 0, 0 over 0.5. 0. Well, what is 0 over 0.5? It's 0. So that's not a change. Now, how about 1, 1? This is going to be 1 divided by 0.5, comma 1. Well, if you put that in your calculator, you'll see that that's 2. But the y coordinate stays the same. Now, here we'll have the x coordinate divided by 0.5, but the y coordinate stays the same. 2 divided by 0.5 is 4. So the x coordinates are getting dragged to double where they were before. But the y coordinates are staying the same, which makes it look lower. There. Yeah. Okay, now we're going to horizontally shrink. And this graph will be black. No, not second. Math. Num. Abs. Did I say 5? What did I say I was going to write? 5x, yes. Okay. So not 0.5x, but 5x. Here's what's happened here with that 5. Zero, zero from the original has become 0 over 5. 0, which is still 0, 0. So it doesn't change. 1, 1 has become 1/5. 1/5 1. Well, it's still 1/5 1. I mean, there's no change. 1/5 1. Notice that it's much smaller. The x coordinate is much smaller than it was before. It's shrinking. But the y coordinates stay the same. And over here we have 2, 2, but the 2 in that position is divided by 5. I'll give you the decimal, that'll make more sense. Okay, 1/5 is 0.2. 0.20. 0.2 is much smaller than 1. And 2/5 is 0.4. 0.4 is much smaller than 2. So here you've got 1 is now in here, but the y coordinate is the same. So see, it's like that and like that. So that it's horizontally shrunk, which in this particular graph resulted in it being, well, taller, skinnier. Hard to come up with words sometime. Those are the transformations. There are a lot of, but we're out of time. So make flashcards of all this. I'll have the video up as fast as I can in the notes, and you will be able to prosper thereby. Okay. I'm back. That was our lesson today. Transformations. It takes work to remember all this stuff. Questions? Okay. Well then, I am going to stop recording.